In the realm of computer vision, image segmentation is a crucial task that enables object recognition and understanding. So, mastering the latest segmentation techniques is a prerequisite for solving complex problems in diverse industries. So, today we will explore UNet, UNeTR, SegNet, Attention UNet, VNet, Swin Unitar, and DeepLab based techniques. So, let's get started with UNet. Now this UNet is a neural network architecture used for image segmentation. So imagine a photograph of a busy street with pedestrians, cars and buildings. Now here the UNet goal is to identify each object in the image and separate them into different regions. And UNet achieves this by using convolutional layers and skip connections, allowing it to effectively combine information from different layers. So first it has encoder. Now the initial part of UNet process the image and extract features through convolutional layers. So it will capture the overall scene and the details. Then it has some skip connections. So UNet incorporates the skip connections which directly pass features from the encoder layers to the corresponding decoder layer. Now this allows the network to maintain high resolution information and effectively combine information from different layers. Then it has a decoder. Now the final part of UNet will reconstruct the original image size and segment it into different regions using transposed convolutional layer. And finally it shall have an output. So UNet will produce a segmented image where each pixel corresponds to a specific object or region. Now this UNet's powerful architecture combining convolutional layers and skip connections enables it to accurately identify and separate objects within the image. So let's take a simple Python code for UNet. Now this code will define a UNet architecture using a Keras library and trains it on a binary image segmentation task. So here first the necessary Python libraries and the Keras package are imported. Then a UNet architecture is defined using UNet function. So this function takes an input shape as an argument and returns a Keras model. So it consists of an encoder, a bottleneck and decoder. Now the encoder and decoder parts consist of convolutional layers with pooling and transposed convolutional layers respectively. So this encoder will capture the features of the image while decoder will reconstruct the output by upsampling the feature maps. Now then UNet model is then instantiated with the input size of 256 into 1. Now then the compile method is used to configure the model for training, specifying the optimizer, loss function and evaluation metrics, and then a getTrain function is provided as an example which generates random training data. So you would need to replace this with your actual data. Then the model is trained using the training data by calling the fit method, specifying the number of epochs, input data and target labels. And finally, a prediction on a new image is demonstrated by passing a randomly initialized image to the trained model. So note that you need to ensure that this new image is appropriately shaped with the batch dimension added. So to summarize this, we can say the code defines a UNet architecture, trains it on a binary image segmentation task and demonstrates how to make a prediction using a trained model. Then comes Attention UNet. Now this Attention UNet is a neural network architecture that incorporates attention mechanism to improve image segmentation performance. Now this Attention UNet leverages the strength of UNet architecture while introducing attention mechanism that allows the network to selectively focus on important regions of the image. So imagine a photograph of a cluttered room with various objects such as furniture, people and personal belongings. So the goal of Attention UNet is to identify each object and segment them accurately. So by incorporating attention mechanism, Attention UNet can selectively focus on important regions of the image such as object of interest while suppressing less relevant information. So it will also have the encoder. Now initial part of Attention UNet will process the image, will extract the features through convolutional layers, then it will have attention modules. Now this attention modules are introduced to the UNet architecture And these modules allow the network to selectively focus on important regions of the image by computing a weight for each pixel. Then we have some skip connections and decoder. So similar to the original UNet, attention unit incorporates skip connections that directly pass features from encoder layers to the corresponding decoder layer. And then the decoder will reconstruct the original image size, segmented into different regions using transposed convolutional layer. And finally we shall have output. So attention unit will produce a segmented image where each pixel corresponds to a specific object or region. So by incorporating this attention mechanism, attention unit can selectively focus on important regions and suppress less relevant information, which allows the network to achieve improved segmentation accuracy, especially when dealing with complex scenes or images with overlapping object. Then comes UNeTR or unit transformer. Now this UNeTR is a novel UNet inspired framework that utilizes a transformer encoder for medical image segmentation task. So here the input image is first divided into non-overlapping patches and projected into an embedding space using a linear layer. Now these patches are then fed into transformer encoder, which uses self-attention mechanism to learn contextual dependency. Now this UNeTR encoder is composed of multiple transformer blocks, each containing a multi-head self-attention layer, position-wise feed-forward network, and layer normalization. So the transformer encoder outputs a sequence of embeddings that are then reshaped into patches at different resolution. And at the bottleneck of encoder, a deconvolutional layer increases the resolution of feature map by the factor of 2. And then the resized feature map is then concatenated with the corresponding patch of the previous transformer output and processed through a series of 3x3x3 convolutional layers followed by a deconvolutional layer. And the process is repeated for all other layers up to the original input resolution. And the final output is then fed into 1x1x1 convolutional layer with a softmax activation function to generate voxel-wise semantic prediction, completing the UNeTR architecture. So this framework combines the strength of transformer models and UNet architecture for efficient and effective medical image segmentation. Then comes the VNet. Now this VNet is a type of fully convolutional neural network architecture designed specifically for volumetric medical image segmentation task. And it is a deep learning based method that uses a series of convolutional layers, max pooling layers and deconvolutional layers to learn features from medical images and produce a volumetric segmentation output. So imagine you have a 3D CT scan or MRI scan of the patient liver, and your goal is to automatically segment the liver and the tumors within it. So this is a typical volumetric medical image segmentation problem, and VNet is a suitable method for this task. Now this VNet architecture consists of a contracting path, that is the encoder, and an expensive part, that is decoder, similar to the UNet design. Now this contracting path captures the high level features by progressively downsampling the input, while the expensive path will reconstruct the special information by upsampling the feature maps. So the key features of VNet includes skip connection, because the VNet uses skip connections which passes information from the corresponding layers in the contracting and expensive path. And these connections helps to transfer the high level features learned in the encoder to the decoder, allowing the network to maintain the special resolution of input and produce a high quality segmentation output. Then we have rectified linear units. Now we know that VNet uses rectified linear unit as the activation function, which is a common choice in deep learning task. Now this rectified linear unit are computationally efficient and introduce non-linearity in the network, allowing it to learn complex features. Then we have dilated convolutions. Now this VNet employs dilated convolution, which are the convolutional layers with a dilated kernel. And these layers allow the network to process a large neighborhood of the input without significantly increasing the number of parameters and computational complexity. Then we have asymmetric skip connection. Now the skip connection in the VNet are asymmetric, meaning they pass information from encoder to decoder in both directions. So this design choice helps us to balance the information flow between the encoder and decoder and produce better segmentation results. And this VNet is designed to be computationally efficient while maintaining high performance in volumetric medical image segmentation task. And the use of skip connection and dilated convolutions allow VNet to process large input volumes with a reasonable number of parameters and computational cost, making it an attractive option for medical imaging applications. Next comes SegNet. Now the SegNet is a deep convolutional neural network architecture designed for this image segmentation task, and it is based on encoder-decoder structure, where the encoder captures high-level features and decoder reconstruct the special information to produce the final segmentation output. Now this encoder and decoder are connected by skip connections which pass information from the encoder to the corresponding layers in the decoder. So imagine you have a two-dimensional image of a natural scene and your goal is to automatically segment the foreground, that is the buildings and trees, from the background. So SegNet is a suitable method for this task, and the key features of the SegNet will be encoder-decoder structure. So the SegNet follows an encoder-decoder architecture. So this encoder will capture high-level features while decoder reconstruct the special information to produce the segmentation output. And the encoder and decoder are connected by skip connections which pass information from the encoder to the corresponding layers in the decoder. Then we have convolutional layers with batch normalization. So SegNet uses convolutional layers with batch normalization, and this batch normalization normalizes the activation of each mini batch, making the training process more stable and less dependent on initialization. Then we have parametric rectified linear unit, because SegNet uses this parametric rectified linear unit as the activation function, and which are a generalization of ReLU that allows a learnable scalar parameter to control the leaky behavior of ReLU. Then we have fully convolutional design. So SegNet is fully convolutional, meaning it uses convolutional layers for both feature extraction and reconstruction. And this design allows SegNet to process images of arbitrary size without the need of additional parameters. And then we have encoder-decoder skip connection. So SegNet skip connection transfer information from the encoder to the decoder. And these connections pass the feature maps from the encoder convolutional layers directly to the corresponding layer in the decoder, allowing the decoder to benefit from the rich feature representation learned by the encoder. And this SegNet is designed to be computationally efficient while maintaining high performance in image segmentation task. Now this use of skip connection allows SegNet to maintain the spatial resolution of the input image and produce high quality segmentation output with a reduced number of parameters and computational cost. And this makes SegNet an attractive option for various image segmentation applications. Then comes Swin Unitar. Now the Swin Unitar is a deep neural network architecture that combines the strength of Swin transformer and UNet architectures for image segmentation tasks, specifically for brain tumor segmentation in MRI or magnetic resonance imaging. Now this architecture consists of backbone, that is the Swin transformer, a feature pyramid volume, and a decoder. So imagine you have a two-dimensional MRI image of a brain and your goal is to automatically segment the tumor regions within the image. So Swin Unitar is a suitable method for this. First, it will have a backbone. So the backbone of Swin Unitar is Swin transformer, which is a transformer-based network originally designed for image classification. Now this transformer architecture is well suited for image segmentation tasks because it can capture long-range dependencies between the input image. Then we have feature pyramid module. Now Swin Unitar employs a feature pyramid module that aggregates features from different layers of the backbone. And this allows the network to capture features at multiple scales, which is essential for accurate image segmentation. And then we have a UNet decoder. So Swin Unitar uses a UNet style decoder to reconstruct the special information and produce the final segmentation output. Now this decoder consists of transposed convolutions, which increase the spatial resolution of the feature, and skip connections that merge the high resolution feature with the corresponding features from the fully pyramid network. Then we have dilated convolutions. So Swin Unitar employs dilated convolution in the decoder, which allows the network to process a large neighborhood of the input without significantly increasing the number of parameters and computational complexity. Also, we have asynchronous processing. So this Swin transformer or the Swin Unitar uses a asynchronous processing strategy where the patches from the input image are processed in parallel. And this strategy enables Swin Unitar to efficiently process large images and reduce the computational cost. So the Swin Unitar is designed to be computationally efficient and effective for brain tumor segmentation in MRI images. And the use of Swin transformer backbone, feature pyramid module and UNet decoder allows Swin Unitar to capture long-range dependencies, process features at multiple scales, and produce high-quality segmentation output with a reduced number of features and computational cost. And this makes Swin Unitar a promising method for brain tumor segmentation in MRI images. Then comes DeepLab. Now this DeepLab is a deep learning architecture designed for semantic image segmentation task. So this architecture utilizes deep convolutional neural networks, attribute convolutions and fully connected conditional random fields to achieve accurate and efficient image segmentation. So imagine you have a two-dimensional image of a city and your goal is to automatically segment the different objects within the image, that is building, roads and trees. So DeepLab is a suitable method for this task. So the key features of DeepLab will be a convolutional neural network, that is a DeepLab uses a deep convolutional neural network as the backbone for feature extraction. So the scene and process the input image, generates a feature representation that captures the high level semantic information. Then we have attribute or dilated convolution. Now this DeepLab employs attribute convolutions, also known as dilated convolutions. Now this attribute convolution allows the network to process a large neighborhood of the input without significantly increasing the number of parameters and computational complexity. And this is achieved by increasing the convolution's effective field of view without increasing its spatial resolution. Then we have encoder-decoder architecture. That is, the DeepLab follows encoder-decoder architecture similar to the SegNet, where the encoder captures high-level features while decoder reconstructs the spatial information to produce a segmentation output. And this encoder and decoder are connected by skip connections which pass information from the encoder to the corresponding layers in the decoder. Then we have fully connected CRF, that is a DeepLab uses a fully connected conditional random field as the post-processing step. Now this conditional random field is a graphical model that models the joint probability distribution over the possible label configurations of the image. This conditional random field helps refine the segmentation results by considering the relation between neighboring pixels. And then we have a large field of view. Now this DeepLab's attribute convolutions and encoder-decoder architecture allow the network to have a large field of view, which enables the network to capture contextual information from a large neighborhood of the input, leading to improved image segmentation performance. So this DeepLab is designed to be effective for semantic image segmentation tasks, providing accurate and efficient segmentation results. And the use of attribute convolutions, encoder-decoder architectures, conditional random fields allow DeepLab to capture contextual information, refine the segmentation results and produce high quality segmentation outputs with a reduced number of parameters and computational cost, which makes DeepLab a promising method for various image segmentation applications. Then comes the summarization of all the UNet based architectures. So first is the UNet, which is the encoder-decoder architecture for image segmentation task. It uses skip connections between the encoder and decoder to preserve spatial information and improve performance. Then comes UNeTR. Now UNeTR is a modified UNet architecture that incorporates a transformer based backbone, that is Swin transformer for image segmentation, which allows UNeTR to capture long range dependencies within the input image, leading to improved performance. So UNeTR also improves or also employs a feature pyramid module and dilated convolutions in the decoder. Then we have SegNet. Now this SegNet is an encoder-decoder architecture for image segmentation task. It uses dilated convolutions in the encoder to capture contextual information while keeping a small spatial resolution. And the architecture also incorporates skip connections between the encoder and decoder to preserve spatial information. Then we have attention unit. Now this attention unit is a modified UNet architecture that employs attention mechanism. Now these attention mechanisms help the network focus on relevant features for segmentation, improving performance. Then we have VNet. VNet is a fully convolutional network architecture for image segmentation which uses skip connection between encoder and decoder to preserve spatial information and improve performance. Then we have Swin Unitar, which is a modified UNet architecture incorporating transformer based backbone, that is Swin transformer, and a feature pyramid module for image segmentation, which allows Swin Unitar to capture long range dependencies within the input image and process features at multiple scales. So this Swin Unitar also employs dilated convolutions in the decoder and an asynchronous processing strategy to reduce computational cost. And finally, we have DeepLab. Now this DeepLab is an architecture designed for semantic image segmentation. It utilizes a deep convolutional neural network as the backbone for feature extraction and employs contextual information. So DeepLab also follows an encoder-decoder architecture with skip connections and then uses fully connected conditional random field as a post-processing to refine the segmentation task. So each of these architectures has its own unique features and design choices tailored to address specific image segmentation task. And the choice of architecture depends on the specific requirement of the application and the available computational resources. Thank you.